Hi, this talk is about our paper Compound or Term Features, analyzing salience and predicting the difficulty of German noun compounds across domains, which is presented on StarSim 2021. Let me first briefly give you an overview about the following talk. I'll first introduce you to German closed compound terms that are the main underlying concept of the paper, and I'll explain our motivation behind investigating their degree of difficulty. While some of our assumptions are already reflected in related work, our study comprises an in-depth empirical analysis of how compound and term attributes influence difficulty. I'll describe the three-domain dataset and gold standard we use, and the experiments we perform with two different classification approaches and several features. The experimental results finally let us better understand what kind of features influence compound term difficulty. As German closed noun compound term difficulty is quite a clumsy expression, I break it up here and explain its parts. First of all, we are talking about terms, which can be defined as the expressions that make up the vocabulary of a specific domain. For example, the expression drill bit can be considered as a term of the domain DIY, or do-it-yourself. Secondly, we are talking about German closed compounds. Closed compounds are complex expressions that are written in a single string of characters. Noun compounds are then the compounds that are only made up of nouns. An example for German closed noun compound is Bremsflüssigkeit, brake fluid, which is a composition of Bremse, brake, and Flüssigkeit, fluid. Last but not least, term difficulty is under investigation in this study, and can be seen as a gradual attribute reflecting how well known a term is to the lay reader. For example, a newbie to the domain of cooking might still know the verb to boil, since it's a commonly known concept. To blanch, however, will not be familiar to a lot of cooking lays, since it is a rather specific cooking process. Now, when it comes to compound terms, there are several ways how difficulty can arise, either through a term or a compound attribute. Let's consider the two compound term examples. Hydraulikleitung, hydraulic line, which is made up of hydraulic, hydraulics, and Leitung, line, and Blaukochen, blue boiling, which is a composition of blau, blue, and kochen, boiling. For hydraulic line, the difficulty comes from hydraulics, which is a rather specific term and thus more difficult. Therefore, it is a term attribute that triggers difficulty here. On the other hand, hydraulics is only one part of the compound, and the second part, line, is quite understandable. Therefore, you can see it is also a compound attribute. In contrast to hydraulic line, for blue boiling, both components of the compound are easy to understand. Nevertheless, the whole compound is quite domain-specific and thus hard to understand for lay people. Here, the difficulty arises because the compound is non-compositional. To sum up, we hypothesize that compound term difficulty is both a result of term attributes and of compound attributes, a hypothesis we want to explore with our following experiments. When it comes to other research on term difficulty prediction mostly focused on the medical domain, which might be a special case in our view since there are many Greek and Latin terms. This is why we focus on a more diverse set of domains. While the comparison of term in contrast to compound attributes has not been explicitly addressed for compound term difficulty, as to our knowledge, it has a long history for term extraction. Both contrastive measures reflecting term attributes as well as approaches reflecting complex terms composition attributes have been introduced in the past. For contrastive measures, a term's occurrence in a domain-specific corpus is compared to its occurrence in the general language corpus. Now, coming to data and gold standard. As already mentioned, we base our study on three domains: cooking, DIY, and automotive. We use corpora that are made up of both expert and user-created content, such as manuals or Wikipedia. In order to compute contrastive measures, we also use the web crawl corpus DEWAG as a general language reference corpus. Our gold standard then is made up of 1030 compounds that are retrieved from the respective domain corpora. We asked 20 lay annotators to rate them on a scale from 1 easy to 4 difficult. We create 2 versions of a gold standard from that. A binary one, where we take the majority voting of 1 easy versus the other 3 ratings, as a division into completely easy and somewhat difficult. For the other version of the gold standard, we remain with the 4 classes and take the median. For our experiments, the goal was to automatically predict the compound difficulty based on features that were computed on the 3 domain corpora. The experiments can be divided into 2 parts. Decision tree classification with handcrafted input features that reflect term and compound formation attributes. Decision trees allow for a detailed analysis of how features interact. We also experiment with neural classification, which means that we use a logistic regression and multi-layer perceptron setup and used word-to-vec and fast text, compound and constituent embeddings as input. For the decision tree classification, 3 groups of features were computed. First, compoundhood features that shall reflect the composition of a compound. For example, the productivity of the modifier is used as a feature here, which is a count in how many different compounds the first constituent occurs. As termhood features, we use the contrastive features that were mentioned earlier. Last but not least, the FGM score can be seen as both a compound and a termhood feature, since it's a measure that combines compound and termhood attributes. Note that when the measures are applied in all the various settings we have for our study, the measures cannot be separated that clearly anymore. The example I gave beforehand also showed you that. To give another example, a contrastive measure can be applied for a component of a compound, which also makes it a compoundhood measure to some degree since it's about the component. Coming now to the results, we first determine the best individual feature. For the binary gold standard setting, this is pure general language frequency of the compound. But when it comes to the more granular 4-class scenario, the compoundhood and termhood feature FGM turns out to be the best feature. In a second step, we analyze feature groups. For the binary setting, all features computed on the level of the compound perform best, while for the 4-class setting, contrastive features are the best. It is to note that the general language features are more dominant for the binary class than for the 4-class task. For the 4-class setting, contrastive features are significantly better than general language features. This shows the importance of termhood attributes for difficulty prediction here. Finally, in another experiment, we only looked at the extreme values of compound frequency and its constituents' productivity. There is a clear picture regarding the results. In all settings, we achieve the best results for the extremest lowest values and not for the high ones. So you can see that here. So all that is in bold is the better result for the low values. In our second kind of experiments, we used neural networks and word embeddings to classify compound term difficulty. We used 3 different inputs: the concatenation of constituent vectors, the compound vector itself, and the concatenation of the constituent and the compound vector. The general picture here is that only taking compound vectors is significantly better than only using constituent vectors as input. Compound and constituent vectors again perform better than only using compound vectors. To sum up the results, regarding compounds and their constituents, a combination of compound and constituent features leads to the best results. Concerning termhood, for the 4-class task, contrastive features perform significantly better than general language features. For the low versus high experiment, which gave us this clear picture, low productivity and frequency consistently lead to better results. Our interpretation is that if one constituent is difficult, and thus might tend to have low frequencies and productivities, this makes the whole compound difficult. If one constituent is easy, the other constituent can still be difficult, which could make the compound still to be difficult. This is why low frequencies more clearly indicate difficulty. To conclude, we investigated the automatic prediction of difficulty for domain-specific German compounds across 3 domains. All in all, we find that compoundhood and termhood features play a role for compound difficulty, although this becomes more evident in the more fine-grained for-class setting. For the broader binary distinction into easy and difficult, difficulty is reflected in the general language frequency of a compound.